Hello, welcome back. We are on our fourth and final lecture in Chapter 5 of Fundamentals of Inorganic Glasses. Up till this point, we have dealt with oxide glasses, and today we're going to turn our attention to non-oxide glasses, which are more specialized types of glasses that do not include oxygen. So let's start off with chalcogenide glasses, also known as chalcogenide glasses. My advisor always said chalcogenide, and so that's what I usually follow. But if you start over here with oxygen in this column of the periodic table and just go downward from there, below oxygen, you'll see sulfur, and then selenium, and then tellurium. All of the elements in this column here would have a coordination of 2, but they're getting progressively larger and larger. A chalcogenide glass is a glass that is based, instead of on oxygen, it's based on one of these other chalcogen elements, usually either sulfur, selenium, tellurium, or some combination of 2 or 3 of them. And more often than not, they are mixed with other elements. If we go over to the left in the periodic table, other elements that are commonly incorporated into chalcogenide glasses include arsenic or antimony. Arsenic and antimony both have a coordination number of 3, and germanium is also quite common to incorporate, and germanium has a coordination number of 4. Now, as we saw in an earlier lecture on topological theory of glass formation, one of the key properties of chalcogenide glasses is the average coordination. The average coordination number of the glass is calculated just as a weighted sum using the mole fraction of each element that's in the glass multiplied by the coordination number of those particular elements. And so if you've got glasses that have a greater concentration of chalcogen elements, sulfur, selenium, and tellurium, with a coordination number of 2, those glasses would have a lower overall average coordination number. Or if you start to incorporate more germanium, arsenic, or antimony, the average coordination number will go up. And if you will recall from that lecture, there is a certain critical value of the average coordination number known as the rigidity percolation threshold. That is an average coordination number of 2.4. And according to Phillips's topological constraint theory, if you have a chalcogenide glass with an average coordination number of 2.4, that would be an ideal glass structure because the number of degrees of freedom in the system are exactly equal to the number of constraints. Now, what are some of the properties of chalcogenide glasses? They have some very interesting optical, electrical, thermal, and mechanical properties. Probably the most important property of chalcogenide glasses is that they have low loss optical transmission in the near and mid infrared wavelengths. And the larger the atoms that you use, the longer the wavelengths that you push out this low loss transmission window. In addition to their low loss transmission in the infrared, they also have a high optical nonlinearity in the infrared. This means that the refractive index of these glasses increases with a higher intensity of light. And because of this change of refractive index with the changing intensity of the light, that means that chalcogenide glasses can be used as optical switches in the infrared. From an electrical property point of view, the glasses could be an electrical insulator if they're based on sulfides. They could be a semiconductor if they're based on selenides, or even a conductor if they're based on tellurides. And so the band gap can change quite a bit depending upon which elements are being used. All chalcogenide glasses have a fairly low glass transition temperature, could be as low as room temperature in some cases, or somewhat above room temperature, say a couple hundred or 300 degrees Celsius. Because of the low temperatures that are involved with forming, they can actually be formed through injection molding, which is a process that is normally associated with polymers. And this process can also be used for chalcogenide glasses. And as we covered in the lecture on Phillips's topological constraint theory, there can be some critical behavior observed in the properties of chalcogenide glasses about an average coordination number of 2.4, where 2.4 is the isostatic system, where the number of constraints is equal to the number of degrees of freedom. If the coordination number is higher than that, then the system is over-constrained. If the coordination number is lower than that, then there are floppy modes in the system as it is under-constrained. And one of the interesting things is that you can continuously vary the properties of chalcogenide glasses by adjusting the composition. That doesn't require a certain ratio of chalcogen elements. You can continuously vary them because the bonding is mostly covalent in these systems instead of a mixed ionic covalent bonding that you'd get in oxide glasses. This figure shows a transmission window for various types of glasses here as a function of wavelength. Silica has really good transmission across the visible, of course, and a little bit into the infrared. As you go down the periodic table from oxygen to sulfur, with sulfide glasses, this pushes the low loss transmission window out to around 10 microns or a little bit longer. And if you go from sulfides to selenides, you're making the atoms even larger, which means that they're going to vibrate at lower frequencies. And this pushes the low loss transmission window out to about 15 microns. And if you go to tellurides, you can push it out to about 20 microns or so. And so the larger the atoms that you use, then the further you push out the infrared absorption edge. And the interesting thing is if you look at these glasses, say this is a telluride glass that appears to be black because it's absorbing in the visible. You can see that over here that this is absorbing in the visible part of the spectrum, which is why it appears black. So if you look at it with visible light, you can't see through it. But if you look at it with an infrared camera, looking at the infrared transmission, indeed, you can see the infrared radiation from this person's hand being transmitted through the telluride glass. So really interesting from an infrared optics point of view, also from an electrical semiconducting point of view. In terms of the glass forming regions, the guiding principle is really Phillips's constraint theory and trying to design the glass composition to be near that isostatic region where the number of constraints is equal to the number of degrees of freedom. That being said, you can still form glasses across a pretty wide range of compositions in the under-constrained and even a bit into the over-constrained regions. Pure selenium on its own forms a pretty good glass. Out of the entire periodic table, the best elemental glass former is in fact selenium. So selenium on its own will form a glass, and it will form a more stable glass if you add something else to it, like antimony or germanium in this case, to get some more cross-linking to help approach an isostatic configuration. And these shaded regions show some of the regions of preferred glass formation for several of these ternary systems. Structurally, the chalcogenide glasses basically follow the coordination numbers of the elements that constitute the glasses. So sulfur, selenium, and tellurium have a coordination number of 2, and so they form these chain segments in the glass structure. Arsenic and antimony have coordination numbers of 3, so they provide a greater degree of connectivity of the glass network, obviously including something like arsenic or antimony or germanium, which increases the connectivity of the glass network, will act to increase the viscosity of the glass and therefore increase the glass transition temperature. Germanium is coming in with a 4-fold coordination, and basically you can have any type of connectivity in this glass where the coordination number is governed by which column of the periodic table that it's in. One of the biggest questions about chalcogenide glass structure is the bonding in the glass truly random? And if you have all of these different atoms in there, is the bonding among them truly random, or is there some degree of chemical ordering in the bonding? And so this kind of presents two extremes, with either having a fully random network or a fully chemically ordered covalent network where there is well-defined bonding preferences. For example, if we consider this arsenic selenide system here and look at, say, the number of bonds as a function of the atomic bond fraction, this A2B3 would correspond to this AS2SE3 system. But now if we vary the mole fraction of these two species here, the arsenic versus selenium, the solid lines show what if you had completely random bonding. So if it's just by chance, there's no energetic preferences in the type of bonding, just making random connections between atoms, you would get the structure of the glass as indicated by the solid lines shown here, where this is indicating bonding between like species of B. So this would be selenium to selenium bonding. The A to A bonding would be arsenic to arsenic bonding. And then the A to B bonding would be arsenic to selenium bonding. On the other hand, if you had a purely chemically ordered covalent network, what this means is that there is an energetic preference for one type of bond versus another type of bond. For example, what if bonding between unlike species is preferred? That means that the arsenic would prefer to bond to selenium and rather than bonding to itself, and the selenium would prefer to bond to arsenic rather than bonding to itself as well. And that would give this different extreme behavior here, which is the dashed lines showing that if you have pure chemically ordered covalent networks, that you'd get this different type of scaling. So if you see here, for example, this type of bonding between unlike species, arsenic to selenium, you'd have a lot more of that in the chemically ordered case compared to the random case. And of course, as you might expect, the truth falls somewhere in between the two, and it depends on the particular chemistry of interest and as well as the thermal history of the glass. If you cool the glass quickly and freeze at a high fictive temperature, a higher fictive temperature would prefer a more random covalent network. If there is an energetic preference for certain types of bonding, then a lower fictive temperature allows the system more time to find those bonds and to restructure the glass network to get to those preferred bonds. And therefore, you'd approach something closer to chemical ordering for a lower fictive temperature. This shows an example of a computer simulation of a selenium tellurium glass. Here you can see that both selenium, which is shown in the gray, and tellurium, which is shown in the aqua color, they're both two coordinated because they're both in that same chalcogen element column of the periodic table. But there is a preference for bonding between like species, meaning that selenium prefers to bond to selenium and tellurium prefers to bond to tellurium. So even though they both make chain-like structures, the chains or the glass structure seems to be segregated at the chain level, where there are selenium chains and tellurium chains that are interwoven with each other. And so there's not as much mixing within the chain itself. Now, the next family of non-oxide glasses of interest are metallic glasses, also known as glassy metals. These are metals with non-crystalline glassy structure. I can't tell you how many times I've heard the question, are metallic glasses transparent? The answer is no, they are metals, so they are not transparent. Metals have, metallic glasses, just like crystalline metals, have the sea of electrons that are shared among atoms. There is an overlap between valence and conduction bands, which means that metallic glasses, just like crystalline metals, will absorb and reflect the incoming light, and therefore they are not optically transparent. Um, so why do we care about metallic glasses? We care about them because they've got some really interesting mechanical properties, and that's because of their glass structure, they do not have any crystalline imperfections. So metallic glasses are formed by quenching from the molten state. It can either be quenched by melt spinning if you need an especially high quench rate to prevent the metallic alloy from crystallizing. You can get these kind of ribbons of metals. So this is an example of an alloy with 4 different metals in it. Um, More recently, metallic glass alloys have been formed that are more stable with respect to crystallization, meaning that they can be quenched slower compared to these melt spun glasses. And that gives the opportunity to melt and to make what's called bulk metallic glasses, or BMGs. Bulk metallic glasses are designed to have a greater resistance to crystallization, which means that you can cool them more slowly, which means that you can form larger bulk pieces of these glasses. Um, and what they all have in common is that the structure of the metallic glass, or the bulk metallic glass, is inherited from the structure of the melt. It's the liquid structure that has been frozen in without crystallization. And if there's no crystal structure, that means that there's no crystalline defects. So there's no vacancies, there's no dislocations, there's no grains, there's no grain boundaries. And metals, the mechanical response of most metals is characterized by their crystalline defects. So that's why if you've got dislocations in metals, those dislocations can move in response to mechanical stresses. Grains can move against each other. You can have grain boundary sliding. And what this means is that metals can dissipate energy um, because of these defects in the crystalline structure. So if you take away those defects, now there's no way for the metallic glasses to dissipate that energy. And so as a result, metallic glasses display a lot more elasticity compared to normal crystalline and polycrystalline metals, meaning if you've got like a metallic glass ball, and if you drop it, it will bounce much higher and for much longer compared to a polycrystalline metal. And if you search on YouTube, you can find several videos that show this really interesting behavior of metallic glasses. So some of the key properties of metallic glasses, they have really interesting mechanical and magnetic properties. The mechanical properties are due to the fact that they don't have any crystals. No crystals means no grains. No grains means that there's no grain boundaries and no dislocations. Um, the surface of metallic glasses is also smoother compared to the surface of um, crystalline metals because of the lack of grain boundaries. So you can have more like atomically smooth surfaces with metallic glasses. They also have excellent corrosion resistance, mechanical wear resistance, limited plastic deformation modes because of the lack of dislocations and grain boundaries. That means that there's little energy dissipation. So one of the applications of metallic glasses is for making golf clubs and tennis rackets. They've actually been banned by a lot of professional sporting societies because it's considered to give people an unfair advantage because if you've got a metallic glass golf club, more of the energy that you put into the club is transferred to the ball because it's not being dissipated within the head of the golf club itself. But I believe it's been banned by PGA. Anyway, um, they also have higher electrical resistance compared to crystalline metals and high magnetic susceptibility. So one of the potential applications is for transformer cores. And there could be some improved superconductivity in some cases of metallic glasses. Much more to be explored there. Um, Now, some of the binary glass forming metallic alloys include this particular alloy of gold and silicon. There's also some better performing glasses that are based on zirconium or palladium. You can see the table here that shows some of these binary alloys and alloys containing more elements. Um, Kind of a general rule of thumb with metallic glasses is you want to add more elements to your alloy and select the combination of metals where they have mutually incompatible crystal structures, either because they prefer different types of crystal structures, or there's a big enough size difference that they cannot be substituted for each other within a common phase. And so if you can suppress crystallization, the better that you can suppress crystallization, the better the glass formability that you'll get. And so having a greater number of different elements with mutually incompatible crystal structures is a way to get greater stability with metallic glass forming alloys and therefore be able to cool them at slower rates. Now, there's a lot of active research going on to try to understand the structure of bulk metallic glasses. It's not very well established for many systems, but one of the models is known as the canonical holes model of Bernal, who considered that there are various building blocks of metallic glass structures, basically various types of polyhedra, including tetrahedral units, octahedral units. This one here is labeled as a trigonal prism. This one D is called an Archimedean antiprism. This is capped with a half octahedra at the bottom and the top, and then tetragonal dodecahedron here in part E. And basically there'd be a mixture of these different types of polyhedra, and then they would all pack together. One of the models for the packing of these different polyhedral units is called the Voronoi polyhedra model. You can imagine this if you like take a bunch of peas and put the peas into a container and then fill the container with water. The peas are going to absorb the water and basically expand until they can't expand anymore because they've butted up against the interface with the other neighboring peas, and you get these types of polyhedral structures as shown here. And so that is kind of a model for some of these basic structural units in metallic glasses. But like I said, there's a lot of ongoing research in this community. This just shows some of the packing around various metals based on these different types of polyhedral units. The next class of non-oxide, non-crystalline materials are amorphous semiconductors. Amorphous semiconductors include amorphous silicon, amorphous germanium, phosphorus, arsenic, and various compounds of these species, including compounds like this is a cadmium, germanium, arsenic compound. The thing to note about this is that these are not glasses. These are amorphous solids, and they are designated with an A prefix, A for amorphous. Amorphous silicon is not a glass, and this should not be confused with glasses. If you want to make a glass out of silicon, the best way to do that is to add oxygen and make fused silica, or also known as vitreous silica, also known as silica glass. Those all exhibit, they're all the same thing, and they exhibit a glass transition, meaning that the structure of the glass corresponds to the structure of the liquid state, and there's a continuous transition between the two, as we saw on our volume temperature diagram. Amorphous solids do not have a glass transition. They do not have a glass transition because they are not formed by cooling from a liquid. They are usually formed by vapor deposition, and their structure is very different from the structure of the corresponding liquid. Now, these thin film transistors, they are often used in displays like TFTs. They can also be used due to their photoelectric effect, their ability to convert electromagnetic radiation into electricity, so they can be used as the solar cell material in photovoltaics as well. So amorphous semiconductors, even though they're not glasses, they are ubiquitous in electronics and in photovoltaics. Um, there are different models for the structure of amorphous semiconductors. One of the earliest is the Polk model. This was an actual physical model that he built, and he identified different types of configurations of these four coordinated elements like silicon and germanium, where each of the elements here are four coordinated. They can go together in this type of chair configuration. If you use your imagination, this is like the foot of the chair, the seat of the chair, and the back of the chair. And so this is a type of six-membered ring configuration that can exist. Another six-membered ring configuration that can exist if you just take this one atom and then you shift it down below the plane instead of above the plane, you get this type of boat configuration instead of the chair configuration. So different permutations are possible based on different torsional angles that are used here. The bond orientations can be classified as either staggered, as in this case, where you've got kind of a twisting of the bonds relative to each other, where there's an angle here, in this case, an angle of 60 degrees of rotation of this plane with respect to the neighboring plane, or they can be in this eclipsed configuration where there is no alignment of the angles in that case, or some mixture between the two. Now, the last class of non-oxide glass that I want to cover is the most recently discovered glass family. This is the newest family of glass, and it is called a metal organic framework glass. This has a structure that's kind of analogous to the structure of silica. So recall that the structure of silica was based on tetrahedral units, where there's a silicon cation in the center of the tetrahedron, and at the corners of the tetrahedra, we have the oxygen anions. Those oxygen anions act as bridges to the neighboring tetrahedra. The tetrahedra share corners with each other, and then the oxygens act as bridging oxygens. With metal organic framework glasses, instead of having a silicon, we have a transition metal like zinc. Zinc is probably the most commonly used one. Cobalt could also be used. And this is fourfold coordinated. But instead of having an oxygen anion, we have an organic ligand molecule. This can be an imidazole molecule, as shown here, or a benzimidazole molecule, which is the same thing, but with a benzene ring attached to it. And these organic ligand units act as the corners of the tetrahedron, and they act as the bridge to the neighboring tetrahedra. And as with silica, these tetrahedra now with the organic molecules on the corners of the tetrahedra, they are bonded to each other to form the large three-dimensional network where the organic ligand is the bridging unit between them. So some of the interesting properties of these glasses, some of them are actually very stable. They are or can be optically transparent, as shown here. They have exceptionally high Poisson's ratio in some cases. It could be higher than 0.4, which is an indication that they may have high fracture toughness as well. We're still at the very beginning of exploring which chemistries of metal organic frameworks can form glasses, how the glass forming ability scales with composition, and how do we scale this up to form larger size pieces. This is one of the largest pieces that has been made up to this point, and it's just 5 millimeters across. So this is a really exciting area of ongoing research. For our glass grate today, I would like to pay homage to Stanford Ovshinsky, who lived from 1926 to 2012. He was born in Akron, Ohio, to Lithuanian immigrant parents. He actually dropped out of high school with no formal scientific education. Despite that lack of formal technical training, he ended his life with over 400 granted patents, and he founded several companies. His inventions revolutionized batteries, solar cells, liquid crystal displays, fuel cells, and phase change memory devices. he was one of the pioneers of using chalcogenide glasses. He invented a branch of electronics involving phase changes in amorphous materials that is named after him. It's called ovonics. He had a very strong commitment to social justice, especially for minority groups. And in 1999, Time magazine named him one of its heroes for the planet. And The Economist called him the Edison of our age. So he's a remarkable individual. So I definitely recommend learning more about him if you are interested. So to summarize today's lecture, the first family of non-oxide glasses that we covered were chalcogenide glasses. These are covalently bonded glasses, mostly used for infrared transmission and switching. Metallic glasses are optically opaque and exhibit really interesting mechanical properties because of their lack of a crystal structure and therefore lack of crystalline defects. Amorphous semiconductors are not glasses, but they're still ubiquitous and they are used for their electronic properties. And metal organic glasses are the newest family of glasses. All right, thank you for listening. Next time we are leaving chapter 5 and going to chapter 6 to cover some general principles of glass composition, structure, property relationships. All right, thank you, everyone. I will see you next time.